Make sure I've got control. All right. I'll get started. You wanna get started with any introductions?
Sure. First, I'd like to thank you for taking the time. For those who don't know, but I assume you've all seen the posters, Steve Rosenberg is a distinguished lecturer from SPE. And I mean, mashallah, let me say it in Arabic for those. يعني في كذا chapter هم كان عندهم ويبينار معاه وايد امدحوه. فإن شاء الله أتوقع أنكم راح تستفيدون يعني من خبرته، وإذا عندكم أي أسئلة تقدرون تسأله لما يخلص آخر يعني ربع ساعة كذي راح يكون عندنا يعني question answer session. So thank you for taking the time, and we're looking forward to the webinar. Steve, you have the floor.
All right. Appreciate the invite, Ibrahim. Okay, I'll get started. First of all, I want to thank the SPE Foundation, Offshore Europe, and the ASME for funding the Distinguished Lecturer Program. It's a means to disseminate the latest technology throughout the SPE chapters all over the world. Also want to thank the SPE staff for facilitating this virtual lecture. My topic is liner drilling, a simple solution to complex drilling challenges. It took me a while to come up with this title. I'm a subject matter expert in liner drilling, but I always knew it was a simple means, because one trip in the hole can mitigate or solve the drilling issue that's your biggest challenge. Basically, as you'll see in the presentation, the liner is the BHA, made up similar to a conventional BHA, as you know from drilling operations. And you drill the liner in one trip, you're ready to cement, and you have your problem interval behind the pipe. What do we talk about? We'll define liner drilling. Basically, the liner is the BHA that you'll be drilling in. Why would you want a liner drill? To mitigate hole problems such as lost circulation, depletion. The applications are drilling into pressure transition zones, as I mentioned, depletion, lost circulation, wellbore stability, where you can't get pipe down. You might not have to drill your liner in, but you can ream your liner in with a special casing bit on the bottom. Some of the liner drilling systems we'll talk about are the non-retrievable, which is probably run about 95–99% of the time in liner drilling operations. This system stays in the hole. It's sacrificial. And then the other system is the retrievable system. This system, you'll have to pull the BHA out of the hole in order to do the cementing job. Both of these have their inherent advantages and disadvantages, but we'll go into detail on this later on in the presentation. We'll talk about engineering considerations, what types of engineering disciplines are involved. For example, torque and drag modeling, hydraulics modeling, fatigue modeling, things to ensure that the liner drilling system will not fail during the liner drilling operation, because not only do you have to manage the problems downhole you're trying to mitigate, but you're also trying to manage the liner system itself. And last but not least, we've got 5 or 6 case histories that we can see these liner drilling applications in real life. And we'll summarize. First of all, what is liner drilling? The liner replaces the conventional BHA. You can see in this picture on the right, you've got a drillable casing bit on the bottom, pup joint, near bit stabilizer. Basically, the liner is the BHA. You provide stabilization as needed to hold your trajectory, or in case of a retrievable system, to steer the well in a certain direction. You'll have centralizers on the BHA for cement job, just as you would in a conventional casing installation. The liner provides the hydraulic energy to the bit, just like drill pipe, drill collars, stabilizers. You got a conduit to provide the fluid to go to the bit to get you the horsepower you need to drill the formation. It provides mechanical force to the bit. That's how you get the weight on bit. The first few joints of the liner you drill in are going to be somewhat in compression, depending on how much weight on bits you put on there. So, of course, you've got to do your torque and drag modeling to ensure there's no buckling that will compromise the liner drilling job. And very important takeaway, the liner drills and cases the hole in a single trip. This is the main message I want you all to get from this presentation. Talk about some liner system basics for those of you who are not familiar with liners. Basically, a liner is a casing string that is set below the wellhead and not connected to the surface. It can be connected subsequently later with a tieback string. Liner can be set on bottom, or it could be hung off with a liner hanger assembly. There's many configurations to meet the weld demands. For example, in this drawing I've got here on the right, you've got a drilling liner, which is basically an extension of the previous casing string, in this case surface casing, to give you a higher fracture gradient without having to run a complete casing string to the surface. So a drilling liner usually gets you deeper than your previous casing string could get you based on your pressure window constraints. And of course, this casing has to be designed to withstand the loading in case of a well control event at this shoe. Now for production casing, you can run a production liner, basically an extension of the production casing to isolate the reservoir you're intending to produce from. And again, you can always tie this back to surface based on your well construction design. Liners can be cemented or uncemented depending on your local regulatory authorities. The majority of them are cemented, but sometimes we're seeing, particularly in Norway, offshore Norway, where the regulatory authorities are allowing the shale to collapse around the liner or casing, and that in itself is enough isolation to prevent migration of fluids. So sometimes regulatory authorities are allowing you to let the formation collapse around the pipe. In fact, I'm going to be co-chairing in the 2021 drilling conference, IADCSB drilling conference, a session on shale barriers for providing isolation. A simple solution. Liner drilling is very similar to conventional drilling methods in that the liner is the BHA, and you'll see this going on in the presentation. Liner drilling success, the success is determined by how the liner BHA and the wellbore are managed. So not only are you managing the downhole problem, you're also managing the system itself, making sure it won't come apart while you're drilling the liner in the hole. So you've got to do your homework up front. I'm going to spend some time on this slide. Why would you want a liner drill? Get your liner to total depth or planned depth. For mitigation, losses. Most of the liner drilling we do is mitigating loss, circulation, or depletion. Basically, what we see in liner drilling and casing drilling, if you will, is that you've got a larger OD pipe in a hole versus you would have a smaller OD pipe in a conventional drilling application. Because of the close proximity of this pipe to the hole, you get what we call a smearing or plastering effect, mainly in sand shale sequences, because due to the close proximity, your cuttings getting circulating up from the bit are getting plastering into the formation, which gives you, if you will, almost a perfect particle size distribution against that permeable formation. And that's the reason we think we see a lot less losses in casing and liner drilling than we do in conventional drilling. Now, when you get into vugular limes, really, really high permeable formations, you're still going to lose fluid, a lot of fluid, but what we're able to do, due to the close proximity of the casing liner to the wellbore, we're able to manage the annulus or backside fluid level via trip tank pump or a dedicated annular pump. And this is the reason we have great success in getting liners to plan TD while drilling with the liner versus if you try to do it conventional. Because the problem is, even though you're losing circulation through the bit, that's one thing. But when your hydrostatic or annular fluid level drops to a certain level, your formations are going to collapse on you. And that's the mechanism for stuck pipe. Through liner drilling, due to the close proximity of the pipe to the wellbore, you can mitigate this by having a slower rate of fluid drop in the annulus. And I hope you all have some questions on this because it is a real thing. We mitigate wellbore stability. As I mentioned, sometimes you're drilling a well, you drill to TD, but then you have problems getting out of the hole. When you're tripping out of the hole, you're taking a lot of weight, a lot of overload, hook load. And so in order to save several wiper trips, what operators will do is put a casing bit, a drillable casing bit on the bottom of their casing and wash and rotate it to TD versus running another drill string to clean it out. This saves you time, plus the longer you're out of the hole, the more bad things can happen, especially in time-sensitive formations. So reaming with casing or reaming with liners is a solution. Depletion, why would you think liner drilling is a mitigant for depletion? Well, you're able to drill a liner with drill pipe, and you can, depending on the rig size, you don't have to make a connection every 90 to 135 feet, just depending on the size of your derrick. When you don't have to make a connection every 90 to 135 feet, and you've got a depleted sand, that minimizes the connections across the depleted sand. What do you think the mechanism for differential sticking is? It's being stuck on the slips when the pipe's not moving. So the longer you can rotate through that depleted sand, better your odds are to mitigate that depletion. We'll use liner drilling for pressure transition intervals. I've been involved with several of these where operators are drilling from a pressured shale into a depleted zone, and they've tried to do this conventionally. For example, if you have a 15-pound shale overlying, say, a 2-pound per gallon depleted zone, what do you think is going to happen when you drill that drill pipe from the pressured shale into the depleted zone? Well, your formation is going to collapse around you, and you're going to stick your pipe, and now you've got some side tracking operations, and I'll show you some case histories of that. So what operators are doing, they know they're going to stick the pipe. So why not drill a casing or a liner through that through the base of that the pressured shale into the depleted zone, getting about 10, 20 meters into that depleted zone, and then you know the pipe's going to be stuck. In this case, it's not a bad thing. You've planned for it. Now you've got, if you will, a straw connecting through your pressured zone to your depleted zone, and you can cut back that mud weight to drill your depletion zone, say with a lower weight mud or with seawater. Versus if you did it conventionally, you'd have to back off, you'd have fishing operations, all kinds of well issues. Now you've got casing there, you've got sufficient isolation, and you're ready to go about your business. In liner and casing drilling, you keep every foot drilled. Once you've drilled it, you keep it. That's a big deal. Here's one: no rig modifications. Typically, when you go out to drill in a liner, you're going to be using almost the same liner system you would use if you conventionally installed that liner. And there's nothing the rig contractor has to do to modify his rig to accommodate the liner drilling. And last but not least, one trip to drill and case the hole. Let's talk about the non-retrievable liner systems. In this diagram here, you can see a typical setup. You've got a drilling with casing bit on the bottom. Now, it doesn't have to be a drilling with casing bit. If it's your last string, you could put a conventional PDC bit on the bottom here because you're not going to be drilling that bit out. You run a stabilizer, X number of feet above, just depending on your directional profile, your trajectory, float collar, as you would in a conventional liner installation. The chute track's not going to make a difference as to the success of the liner drilling job. This is based on where the operator wants to position his float collars to give you enough room in the chute track for contaminated cement. You've got your centralization as per the operator's plan. You can even run annular casing packers to enhance your cement job. Then you've got your liner hanger packer assembly at the top over here, just as in a conventional operation. These are the most simplest and most common. You have the ability to cement when reaching total depth. This is a big deal. Anecdotally, talking with operators, and I've seen several of these cement jobs, you do get a better cement job when you drill with liner or drill with casing versus conventional. And the reason I think this is, when you're drilling in liners and casing, you typically don't get the jet velocity or hydraulic horsepower through the bit. This jet velocity is directly proportional, if you will, to the amount of washout. Your washout isn't determined by the angular velocity, it's determined by the jet velocity going through the bit. So the higher the jet velocity, the more washout you have. The more washout you have, the less likely you are to have a good cement job. So remember that. The reason is we don't have as higher pump rates when we drill with liners, or for that matter, casing, because like I said at the beginning, you have a narrower annulus. So per unit pump rate with liner drilling, you get a higher annular velocity versus that of a conventional casing installation. And with that higher annular velocity, you get better hole cleaning, albeit at lower pump rates than you would with a conventional installation because of your narrower hole geometry. Sleep on that and ask me if you have any questions. That's a mouthful, but it is a fact. Disadvantage of non-retrievable liner drilling systems: you cannot steer it actively. So all these applications are designed to either maintain the vertical section of the hole or maintain some pre-built tangential angle. For example, if you've established a 60-degree angle, we've proven these non-retrievable liner drilling systems can actually maintain that angle over hundreds of feet. Reason being, it's a lot stiffer. The liner BHA, the liner itself, is a lot stiffer than conventional BHAs. So it's going to be less predisposed to turn in a certain way or build in a certain way. However, there is BHA modeling software that you can design these liner drilling systems to have a build, a drop, or maintain neutrality while drilling. So there is software for that. Another thing is you're limited to cased hole logs. You really can't run open hole logs through here because nothing's coming out of the hole. There are some systems that you could pick up, drill out your casing bit, and then run logging tools through here, but that really defeats the purpose of liner drilling and the problem you're trying to solve. Like I said, you want to keep every foot. So if you have to pick up this bit to log, then you could potentially lose that hole you've already made. Now, on the other hand, retrievable liner systems, Baker and Schlumberger have these. These do have directional capability. You have a pilot BHA here with a pilot bit and an under-reamer attached to the liner itself. Basically, for example, if this is a 9 5/8 inch liner and you're drilling a 12 1/4 inch hole, this pilot bit's going to be about 8 1/2 inches. This reamer is going to be about 12 1/4 inches to allow this 9 5/8 inch liner to pass through that 12 1/4 inch hole. You have your liner tools up here. But the big disadvantage is when you get to TD, you've drilled your well, now you've got to pull this pilot BHA out of the hole. So you could be waiting, 15, 20 hours before you do your cement job. And this in itself could be problematic with attaining a good cement job. Now, the reason an operator would want to run a retrievable liner system, if they do have to do active directional steering, and they do have to run open hole logs while drilling the liner in. Another advantage of the retrievable liner systems is multiple trip capability. Say your MWD or motor fails, you can pull this out of the hole, rerun another BHA. So there's pluses and minuses. You just have to know what your application is. Another thing is the complexity you have to think about with the retrievable liner systems. Not only, as I've mentioned before, not only are you trying to solve the problem with liner drilling, but you're also trying to manage this complex system at the same time you're managing your liner system. So you gotta really have the right application. Very important for liner or casing drilling is the connection design. Why do you all think it's important? The biggest reason is because you're going to be rotating for several thousand revolutions, as we like to call it, K-revs, or 1,000 revolutions. What happens when you rotate for several thousand revolutions? You get some type of decrease in fatigue resistance of your connections, especially in directional holes where you see dog legs over 3 degrees per 30 meters or 3 degrees per 100 feet in imperial units. The higher the dog leg, the less fatigue life you have in these connections. So that's that's where you're going to have failures if you've improperly designed your connection for the liner drilling application. So you want your connection to be proven in liner drilling or casing drilling applications, or make sure it's been run successfully before in the application you're looking at. You want it to have high resistance to compressive, bending, and tensile loads. A lot of mechanical forces, the same forces you would see when you're drilling a conventional assembly in as you would in liner drilling. And the most important right here is high resistance to cyclic stress fatigue. What this is, like I mentioned, you're going to be rotating for thousands of revolution, especially in a dogleg severity, high dogleg severity. You want the connection vendor to provide cyclic fatigue data showing that, in fact, based on the longevity of your liner drilling job, that those connections will hold up based on hole conditions. Very, very important. That's a key takeaway for connection designs. Obviously, you want high torsional resistance because you're rotating the liner. Economic considerations are very important, of course. I know I work a lot in U.S. land applications, and they typically run some type of buttress or modified buttress. But then again, people that run torque rings in buttress or 8-round connections, the torque rings do give you added torsional resistance, but they do nothing for fatigue resistance. So think about that for a section. In vertical holes, you're probably going to be okay because there's less cyclic fatigue resistance than there would be in directional holes. So these two go hand in hand, but you don't want to run a cheap connection where you're expecting high cyclic fatigue issues. And last but not least, you want to ensure your connection integrity. All this design work does you no good if you don't properly make up your connection at the rig floor. So I hope that makes sense to everybody. Very important, connection design. What are some of the design considerations? Directional control requirement. This will dictate a non-retrievable versus retrievable system. Do you need to run a liner hanger, and do you need to run a packer? What you have to think of here and this is tied in with bypass area. Sometimes you don't have to run a hanger. What a hanger does, it reduces your annular flow area, which could increase your chance of packing off. A hanger is invaluable if you have to run a packer, because many of the liner packers are set by mechanical activation. In other words, setting weight down on the liner itself to expand the packer. So you want to make sure, if you don't run a hanger, that the liner won't go into a helical buckling scenario when you do set the packer. Now, as far as a packer, many times we advise the operator to run a packer on the second trip if he can do that. Reason for this is the packer encompasses a lot of hydraulic bypass area, and it could impede your liner drilling operation by making you pump at a slower rate, which could affect hole cleaning and wellbore stability issues. So you really have to take everything into consideration. The setting sequence. Now, I know on expandable liners, the cement is pumped prior to release of the liner setting tools, and in conventional hydraulic system, it's just the opposite. The setting tools are released. So that's a big consideration. A disadvantage of cementing prior to release of the tools is that you could potentially cement your running tools in place and have a fishing operation. And last but not least, you do want your hanger or running tool system of the liner to be pressure balanced, hydraulically pressure balanced. But what I mean by this is many times you're drilling in a liner in hazard conditions, for example, severe loss circulation. So some of these systems are not hydraulically balanced. In other words, if your fluid level drops to a certain level, you have a high pressure differential across that setting tool, and that could prematurely set your hanger and release the running tool. So you want a hanger setting system that is pressure balanced, so this won't be an issue while drilling through lost circulation zones. Talk about liner drilling float equipment. We recommend poppet type float collars. In other words, dart type float collars with a spring mechanism right here versus the autofill type. Now, why do we recommend this? With poppets, they're a lot stronger. We've seen less failures with these than autofill. The problem with autofill is you have a flapper valve right here. If you're drilling with this flapper valve in a closed position, it's exposed to a lot of cycles, a lot of flapping, because the flapper's moving up and down. And just like in connections, it probably has a limited fatigue life, and it could potentially fail. I've personally seen this in 2 liner drilling jobs with the higher mud weights. It gets eroded away, and that coupled with the fatigue failure of the valve, it plugged off everything. We had to pull the liner out of the hole. So the poppet type float collars, just by the look of it, they stand up to liner and casing drilling a lot better than the autofill. Now, in some instances, you will have to run. The operator will dictate they run autofill because of fluid losses. You're running these in a narrow pressure environment, so you do want to have that open as long as possible to reduce fluid losses or surge formation to the formation while you're drilling in. So be careful in the design, but we strongly recommend the poppet valve versus the autofill. As I mentioned before, a shoe track requirement will dictate spacing. This won't impact the success of the liner drilling operation. It's just depending on what your spacing of your flow collar is to house the contaminated cement. Talk about centralizers and stabilization. We recommend solid body centralizers with non-welded blades. Here's an example of a solid body centralizer courtesy of Weatherford. Basically, this is one piece of steel. The blades are part of the body right here, so there are no welds. So it's very robust. You have vent holes at the bottom of the centralizer to allow debris to fall from the inside through the holes, so your centralizer does not lock up or continues to stay in one position while you're rotating the pipe across it. Inside the centralizer, you have a 90 diameter rubber lining with flutes in here to allow fluid. So if you can visualize, you have your casing rotating inside the centralizer. We call this centralizer non-rotating with respect to the wellbore itself. And theoretically, it just slides with the pipe. So with this rubber lining, you have a less coefficient of friction, which in itself reduces the torque. So when you're running the torque and drag models, you can see less torque these versus a conventional one without the rubber here. So this is a very robust centralizer. Now, when you get into tight tolerance situations, for example, running a 9 5/8 inch liner in a 10 5/8 inch hole, for example, or an 11 3/4 inch casing, you really don't want to run a slip-on type centralizer such as this, because the body of the centralizer will encompass much of the hydraulic bypass area. And what this does, it leaves you less rooms for cuttings being circulated up, which increases your chances of pack-offs. So there's a company called Wear Socks. They have a thermally spray application where they actually pump spray molten steel onto the body of the casing, onto the outside of the casing, and it builds up or custom makes the centralizer height to whatever specs you need it to. It does not have a body. The standoff is generated by the blade itself, so you have a lot more hydraulic bypass area here than you would in a centralizer with this design, which makes it ideal in tight tolerance situations, because you've got a lot of hydraulic bypass area, or junk slot area, as some people call it, for the cuttings to circulate through, so you minimize your chance for a pack-off event. Over here, Ace Oil Tools has been kind enough to let me put up their diagram for stop collars. You do want stop collars with high holding capacity, because the last thing you want is the centralizers to move up and down that pipe and break off and cause a bad day ending your casing or liner drilling operation. These designs are designed for over 90,000 pounds of axial loading. So keep that in mind. Stop collars are very important in liner drilling and conventional liner installations itself. Operators like to run with collared casing, like to let the centralizer slide between the collars. For liner drilling, I do not recommend this. As you're moving that pipe up and down, you have a greater chance, or the centralizers move up and down, you have a greater chance of those centralizers failing, breaking off, and bad things can happen. So anchor your centralizers down, put a stop ring plus or minus a few inches above and below, and you'll be in good shape. Again, with a high holding capacity, because you are exposing it to high axial loads. Drilling fluid and cementing design. You want your liner drilling system to be compatible with the lost circulation you're pumping. Now, typically less than 25 pounds per barrel lost circulation material in the system, that's not going to cause you much issues. Where you run into problems is when you have greater than 30 or 40 pounds per barrel concentration with a high concentration of fibrous materials. If the operator wants to run a high concentration of lost circulation material, I strongly recommend to have that lost circulation or mud vendor run design a flow loop where you're pumping that lost circulation concentration through a setup of your liner tools, your bit and float equipment, to make sure nothing will plug off. That's the last thing you want, is to have something plug off while you're drilling a liner and have to pull the whole thing back out of the hole again. So you do want to make sure the lost circulation material is compatible with the liner system you're drilling in. Should have a liner system that can be designed for a 2-plug or 1-plug wiper plug system. Sometimes we'll drill a liner in with a multi-stage cementing capability. This is the same as a conventional liner system. There's mechanical, and now they have RFID, or radio frequency identification enabled intervention, where the advantage of this is it doesn't require any mechanical intervention to activate the stage collar. You activate it through a pressure pulse or an RFID tags. The beauty of this, especially with stage collars, is that there's no pressure surge when you open the stage tool. And this is especially valuable when you're adjacent to a low pressure or a tight pressure window, or any pressure surge could potentially break down the formation. So just something to think about in design of cementing and drilling fluid. Now, very important, obviously, is the casing bit you want to use for liner drilling. The engineers need to do their homework up front. They need to look at offset drilling records, particularly dull gratings, to make sure the casing bit design can drill the required formation. Because the last thing you want is these bits to fail while you're drilling. So we like to look at sonic logs and density logs. Sonic logs, typically transit time readings greater than 65 microseconds per foot, are usually soft enough formations that a casing bit can drill these. Once you get transit time readings less than 65 microseconds per foot, you're looking at formations greater than 20,000 PSI unconfined compressor strength. This makes the design of the bit more complex. You'll see in this diagram right here, a 4-bladed bit. You might have to run a 12-bladed bit, some complex bit, which will hurt the drill out of the bit. Also, another thing with the harder formations, it's going to take a lot longer to drill. It could make your casing susceptible to wear, some type of damage. And I know there's been issues in some of these shale basins where hydraulic fracturing, they say, is responsible for casing failures. Well, you don't want to have damaged casing in the hole prior to fracturing. This could be some type of mechanism for less life of the casing during fracture jobs. I'm showing here 2 bits. This bit on the right, courtesy of Baker Hughes, is a steel bit, alloy steel. It's got carbide nozzles, all of which are drillable with a conventional or PDC bit. It's got steel blades and PDC cutters brazed to the steel blades. Basically a PDC bit, if you will. One thing this bit also has, which isn't shown, it's got a secondary bypass port, and that bypass port is used just in case the nozzles plug off. That bypass port is set for a rupture disc to rupture at a certain pressure, and that'll enable to keep your pumping, or if you do your cement job, keep your cement job going on. This bit on the right is a drillable casing bit courtesy of Weatherford. You can run either ceramic or copper nozzles. The ceramic nozzles are good to about 400 feet per second nozzle velocity. The copper is about 100 foot per second nozzle velocity. It's got aluminum face, aluminum blade support attached to the aluminum face, and on top of the aluminum blades, you have mechanically locked a thin steel rail which houses the PDC cutters. So this bit has been drilled out sometimes less than 15 minutes with a conventional PDC, because it has about 85% less steel in the drill out area than a comparable steel alloy construction. So these are all factors that go into which bit you want to use. Remember, if one vendor has a bit that takes you two hours to drill out, and the other vendor has a bit that takes you 20 minutes to drill out, and you're spending $200,000 per day, that's going to be a factor in your decision. Computational flow analysis, hydraulics modeling, determines the spacing of these nozzles right here. So that's one of the factors the casing bit design manufacturers take into account when designing these bits. And very important here, I put together this liner drilling engineering matrix. On the left axis, I've got operations constraints and liner design. And up here on the x-axis, I've got the engineering constraints. Basically, you want these constraints here with the liner design to fall within the window of your engineering modeling up here. So for example, under operations constraints, you're going to have weight on bit, revolutions per minute, flow rate, standpipe pressure. All that has to fit in under your initial engineering design. Now with the liner itself, the design, the setting system, hydraulic setting system, your connection design, the pipe properties, L80, K55, Q125, etc., and your operating parameters all, again, have to fall in with these engineering constraints. So I thought this was a pretty powerful slide showing the interaction or the interfacing between design parameters and the engineering constraints you'll do in your upfront modeling. Now, on to the meat of the matter, the case histories. Where have these liner drilling applications been done and what type of success? I've taken a snapshot of 5 or 6 liner drilling operations all over the world and broken them down. The first one right here is in the Gulf of Mexico shelf. And the operator had 7 5/8 inch liner at 13,385 feet measured depth. And below this, there was a 17-pound shale and a 2-pound sand. And their objective was to isolate in one trip the shale and the sand so they can enable their 4.5 inch completion or 3.5 inch completion. They tried it first time with conventional means, and what do you think happened? It got stuck, but they did manage to free the pipe, which is very unlikely in most of the cases I've been exposed to. So they decided to try liner drilling. And the hardest thing was deciding, well, what mud weight would you use to mitigate this high pressure shale and low pressure sand? And they come up with about a 12-pound mud weight. And the reason being, based on your equivalent circulating days, is you want a mud weight that's high enough to mitigate the shale from popping off on you and packing you off, but yet low enough that would not fracture or compromise the frac grade of this 2-pound sand. So they come up with a 12-pound sand. They used a water-based mud. They exceeded conventional 6.5 inch hole drilling limits. About 480 foot of a 5.5 inch 23-pound liner reamed and drilled in 113 feet with no fluid losses. They successfully isolated the 2-pound sand and the 17-pound shale, saved a 3.5 completion system, and obtained an 18.3 pound per gallon formation integrity test, a highly successful well. Conventional methods result in stuck pipe, but they drilled the liner in and were very successful and got a successful cement job. This next case, Deepwater, Gulf of Mexico. So liner drilling has been used in land applications, shallow water, and deep water. This was about 6,000 foot of water out in Mississippi Canyon, Gulf of Mexico, offshore Louisiana. The operator had 13 5/8 by 14 inch casing set at 12,900 foot measured depth. The problem was they had this high permeability depleted sand below this casing. And they knew with conventional methods, they would lose all kinds of fluid and probably stick the pipe. So what they did, they evaluated drilling in a 9 7/8 inch 62.8 pound liner to get through this sand and set the liner in a competent shale where they would have a good fracture gradient to eliminate a potential contingency string and enable them to get to their planned TD, which is exactly what happened. They drilled it. The liner was a short one, about 650 feet, but they drilled it in successfully through the sand and did get it into the competent shale, but not before some problems. They lost total circulation once they hit this sand. In fact, they were losing prior to, because they think this sand was connected uphole. They were losing about 280, 290 barrels per minute of fluid right here. And when they got into the sand, it increased to about 350 barrels per minute. And when they got out, it decreased back down to 290. We think this is due to the smearing or plastering effect. The operator had planned for losses of over 1,000 barrels per minute. So they had an armada, several transportation vessels outside off near the rig, just in case it had catastrophic losses. And that wasn't the case. Everybody was pleasantly surprised, probably due to the smearing mechanism sealing off that permeable sand. The liner drilled 306 feet with total fluid losses. But the big thing here was the annulus was kept full using a trip tank and a riser pump. The sand was isolated. They maintained their established 36-degree inclination over the 306-foot interval without any active directional control. Very cool job. And an SPE paper was wrote on that 170290. Third application I've got here is the first liner drilling job done in Romania, OMV. The issue here was isolating a mobile salt. They called it a salt creep interval. They had to get through, they had to run a 7-inch liner through it. So they had a 9 5/8-inch casing set at 41-48 meters. Immediately below it, they had this salt section, and the salt section was only 8 meters, and they had shale below it. So the objective was to get below this salt, isolate it with casing, and go on and drill to TD. But in conventional applications, what do you think happened? It resulted in 3 sidetracks. They couldn't get the pipe through here. They stuck the pipe, had a sidetrack, did that twice. What's the definition? I guess it's Einstein's definition of insanity. Do the same thing over and over again and expect a different result. Some of these cases were exactly that. So they decided to try liner drilling, drill conventionally to the top of the salt with an 8.5-inch hole, pick up a 7-inch liner. And what happened? They drilled that 7-inch liner 7 meters through the salt, and they isolated this 8-meter salt section with the 7-inch liner. They only drilled several meters outside the salt because the bit failed, but that was okay. They isolated the salt, and it was successful, where it saved 3 previous sidetracks. So another application in liner and casing drilling is to mitigate salt movement. Here's one offshore India. This was a CNOC job, I believe. They published a paper on it. Basically, they had 9 5/8-inch casing at about 84, 87 feet. And below this, they had a shale section, a highly permeable limestone, and they had what's called the Gita sand, their production interval. And their objective was in one whole section to get through this interval and land casing 7-inch, a liner, 7-inch liner into the top of this productive Gita sand. As you can see, they tried it conventionally. It resulted in 2 sidetracks. So they went in with a 7-inch, 26-pound liner. In fact, the liner was a chrome liner. This was the first instance of drilling in a 13 chrome liner. This was back in 2007, I believe. They drilled the liner in, all the while sustaining total losses, but they were able to keep the annulus full, unlike conventional applications. They also maintained a 67-degree inclination. They got to TD, got a successful cement job, and were able to drill out the bit and drilled a 6-inch hole to TD. Happy ending to that story. Here's one offshore Mexico. This is a good one. The operator, Pemex in this case, another paper published on it, had 13 3/8 casing set at 57.35. But the problem was they had to isolate a highly unstable shale and a fractured limestone in a single trip. But there's more to it than that. When trying to drill into this fractured limestone by conventional means, they would accidentally get into this limestone because the cap rock of this limestone, where they intended to set the liner, sometimes it would be eroded and they would never see it. So they would be already in this fractured limestone, total circulation loss. This unstable shale would collapse around the drill string. So what they decided to do was drill a 12.25-inch hole, and they established about a 75-degree inclination here. Pick up a 9 5/8 53-pound liner, drill that liner through the base of this unstable shale into the cap rock of this limestone. And even if they drilled too far and sustained severe loss circulation, that was okay, because the shale would collapse around the pipe, and then they would have a string or a conduit into this fractured limestone, and they could drill conventionally with seawater through this tertiary or fractured limestone here. And what happened? They had a geologist on location. They did see the top of this cap rock. The liner stopped right here. No losses sustained. Got a great cement job. We're able to drill out with a seawater and drill through the fractured limestone very successfully. They drilled 266 feet without losses, maintaining a 75-degree inclination after the liner job. Very successful job. Pemex went on to do probably 10 to 12 more of these similar type liner jobs where you had this breccia shale exposed. And the final case history I have, this is a very shallow water Gulf of Mexico application. The operator had 13 3/8-inch casing, about 1,530 feet per their plan. And originally, they did not have this 9 5/8-inch casing set. They wanted to drill through this catastrophic loss zone in a single section. But what do you think happened if they tried to do it conventionally? Resulted in 2 sidetracks, because what would happen? They get into this loss zone, all this shale would collapse around them. It'd be a bad day, they'd have to pull it out. So they decided to change their well construction design and top set above this loss zone a 9 5/8-inch intermediate casing to minimize the distance of a pressured shale and the depletion down here. And also they want to incorporate liner drilling so as not to take the chance of having any exposed shale above here collapse on you while drilling. It's exactly what they did. They drilled a 7-inch, 23-pound liner, about 800 feet in length the liner, drilled about 500 feet through this loss zone, all the while total losses, but they were able to keep the annulus full. They were losing about 20 barrels an hour down the backside. They easily kept the annulus full and obtained a decent cement job. Got an 11.5 pound per gallon formation integrity test, and it worked out really well. So what are the key takeaways for liner drilling? Drilling hazards can be mitigated with a single trip, as shown in these examples I showed you. No rig modifications required. This is a big deal, because why do you want to have to change something on the rig just to put your tool in the hole? You want everything to be compatible as best as possible with the rig that you're going out to run this in. Losses, they're a whole lot more manageable than with conventional drilling, as I've just shown. Why is that? Because you've got a tighter proximity between the casing and the hole size it's being drilled in. And through that smearing effect and through the close proximity, you have less fluid losses down the annular side than you would down in a conventional application. And one trip to drill and case the hole. And that completes my presentation. And I very much look forward to any questions. Thank you very much.
Thank you, Steve.
Welcome.
If there's anyone who has any question, you can raise your hand and we'll give you the floor to speak.
Yes, and even after the presentation, Ibrahim will give you my email, and feel free to email me any questions that you've got.
For sure.
I'm sure you got several questions.
Let's see. Or you can type in the. Oh, okay, here we have a few.
Let's
Okay.
see if I can.
Yusuf Behjet.
Let's see here.
Hello.
Hello.
Yeah. Just I have one question. Actually, when I think about the linear drilling, can we do multiple linear drilling in the same well, or just like vertical drilling? It's only one. Because I'm thinking about it.
You're talking about back-to-back liner drilling jobs?
Yes.
Yes. Yes, that's seen more in casing drilling, but yes, you could do that. I'm not familiar with any applications. It would have to be the right applications, but that could be done. We see it more and more with casing drilling, especially top hole sections, to save money where you have high rig rates, where you drill in the conductor pipe and then follow that drilling in the surface pipe. But in liner drilling as opposed to surface drill, as opposed to casing drilling, it's more designed to mitigate a hole problem. Something like wellbore stability loss, circulation depletion, as I mentioned. So with that said, you can do it, but there has to be a really good reason to do it.
Yeah, I got that. Thank you.
That makes sense?
Yes.
Okay, next up we have Umar Shaban.
Thank you, sir, for your excellent presentation. It was very informative. I just have a couple of questions. The first being, it's regarding how the liner drilling can improve cementing jobs.
Mm-hmm. Yeah.
Now, I get how it can reduce losses and all of that, but I still didn't quite get how it can improve the cementing job. So if you can clarify it more, please, that would be great.
Great question. The number one reason is because you're ready to cement once you reach TD. Think about that. In conventional applications, you drill the hole, then you got to pull your BHA, lay down your BHA, and run your casing in. That could be a 24, 48-hour process. So that's the biggest reason. The other reason is you're drilling more of a not a straight hole, but what we call in the U.S. a gun barrel hole with minimal tortuosity due to the stiffness of the casing. And also, as I mentioned, you have less washout with casing and liner drilling simply because you're not pumping as hard. You don't get the jet velocity, nozzle velocity, or the hydraulic horsepower through the bit. And these are the mechanisms where you see more washout. So if you have more washout, your cement job's probably not going to be as good as a conventional application. Does that make sense?
Yeah, I totally get it now. Thank you so much.
You're welcome.
If I may, I have another question.
Yeah.
Thank you. So you mentioned that liner drilling can solve a lot of problems regarding troublesome formations, and then how we can isolate them immediately while drilling.
Mm-hmm.
But generally, in the case of the liner or the casing itself getting stuck, what happens then?
If the liner gets stuck? Yeah, great question. Well, you're going to try to free it. And in one instance, I can remember, I think it was back in 2012, the liner actually became stuck and the operator pumped a oil-based mud pill. 24 hours later, it was free. Your liner still can become stuck. If you can't free it, you're done for the day. I mean, that's what you have to cement it in place right there. But that said, you probably have a better chance of freeing that liner where it's been drilled in versus a conventional liner installation, because you've got a better hole created by that liner drilling. And I'm saying that anecdotally and from cement bond logs and experience, but you would have a better chance of freeing it. But sometimes you can't free it and you're stuck there. But these are all things, that's a really good question. These are all things that have to be considered in the planning of the job. What we'll usually ask operators are, one of the big questions is, what is your minimum required depth for this liner drilling to be successful? For example, if your goal is to set the liner system at 5,000 feet, but if 4,800 feet is acceptable to mitigate all the problems, once you're past that 4,800 feet, if you start seeing a pack off event or the pipe torquing up on you, whatever, you don't want to work the pipe and potentially lose the hole. You want to keep on going until you get stuck. So there's a minimum acceptable depth at which you do not want to work the pipe anymore. And this has to be between the vendor company that's supplying the liner drilling job and the operator that's paying for the liner drilling job. Does that make sense? I said a lot in a mouthful there, but does that make sense to you?
Yeah, it does. It does. Thank you.
So you have to define, but that said, things can happen. So you have to manage the risks. That's right.
Thank you so much.
Very
One
good,
final
very good question. Yeah.
Thank you, sir. So one final question is, I was just wondering, so we know how the liner drilling can solve a lot of the problems that might be faced during conventional drilling, but what are the specific challenges or let's say drawbacks for liner drilling itself when we apply this sort of approach?
The drawbacks, you could have the wrong casing bit in the hole. What are the other drawbacks? What happens if your connections fail and you haven't designed your connection right? Yeah, you're done. Have to pull it out, or else you got a fishing job. There aren't really that many drawbacks. The biggest thing I can say is improperly designed for the application. If you've done your homework, most of the liner drilling jobs I've been associated with, I've had over a month, 2 months sometimes, in being able to plan this thing, going through all the contingencies. So the biggest drawback, I would say, is an improperly designed job, and the job's not designed for the application. This is a team program with liner drilling. You have to have the rig contractor on board. You've got to have the cementing company, the mud company, the driller, the engineers. Everybody has to be on the same sheet of music, if you will, that to make this a successful job. Go ahead. Was that clear, or are you still confused?
Yeah. No. Thank you. Thank you so much for answering my questions.
There's really no downside if you use it for the right application. Yes, things can happen. Unforeseen things can happen, but you have to do a proper risk assessment to be able to address these things so there are no surprises during the liner drilling application. One of the biggest things, even before you start, you want to make sure that in the bit itself, the first thing you do when you pick that thing up, the bit up, you want to look underneath to make sure the nozzles aren't plugged. You have to, here's something, you bring up a great question. I love those questions. This actually happened in a job I was involved with. They didn't clean the active pits out after they drilled out the float equipment. So we picked up the liner, started going in the hole with the drilling liner, and what do you think happened when they started taking suction out of that active pit? All that debris from the float equipment plugged off the floats. And it was a good thing we only got to about 600 feet below the derrick, and we had to pull the liner out of the hole. We had a backup system. You need to have a backup liner BHA in case things like that happen. That comes to mind. That's a good point I bring up. You want to make sure everybody's on board. You want to make sure you have a clean active pit. There's no way to plug off the float equipment. You want to make sure this lost circulation material is designed and compatible with your liner system so you don't have premature plugging. Basic common sense things some people won't remember. And this was unbelievable. This is a job that the operator had been planning for 2 years, and they didn't clean out the active pit. No names mentioned.
Yeah. Thank you so much, sir, for answering those questions. It's the simple things that can screw up the jobs.
You got it. It's the simple things. But the big thing is you want to have enough time to plan it. Everybody's part of the team. You know, there are no dumb questions when it comes to these complex operations. Everybody's part of it. You want to make everybody part of the team. That's it.
Thank you so much, sir, for answering the questions.
You're welcome. You're welcome. Thanks for the question. Great question.
I have a question as well, and I guess we'll see if anybody else raises their hand, but if not, mine might be the last one. I think you mentioned that there are two kinds of liners, those that can rotate and those that can't.
Okay. Two kinds of liner drilling systems.
Yeah.
The non-retrievable system and the retrievable system. All of them can rotate.
Okay.
Now, Ibrahim, you got a great question. That's a good question. Now in the steerable or the the retrievable systems, you can rotate it with just a mud motor, but the liner itself won't be rotating. Even in that case, you still want to impart some rotation, because rotating the liner is an inherent advantage of liner drilling, like I said, with the smearing effect, that type of thing. So you do want some rotation. If you're going to drill in a liner without rotation, you have to be careful, because it's like sliding. You could create, dog legs like you would in a regular conventional liner horizontal hole drilling application. They say rotary steerable is better than sliding because you're rotating the pipe. It helps you clean up cuttings bed. Same thing really goes for the liner. You get more advantages rotating it. But that said, yes, you could just rotate at the bit and do this thing. Yeah.
And what about the systems that can't move?
The non-retrievable systems.
Yeah, like why would anybody use that instead of the retrievable? Doesn't it seem like
because number one, you don't need the complexity of a steering system, and number two, that will get you to TD. You're ready to cement right away. You can model these non-retrievable systems to give it a slight build or drop. So that gives it that's ideal if all you want to do is maintain the established tangent angle or verticality. It's a lot simpler. It's a whole lot more cheaper, and a lot less things can go wrong. Does that kind of answer your question?
Yeah. So it depends on the case. I mean, if it's not
absolutely, it's the application. Ask yourself: do you need to steer? Do you need to run open hole logs? If the answer to that is no in both instances, then I would go with a non-retrievable system. Now, one thing I didn't mention is how long do you want a liner drill? Most of the liner drilling, if not all, are done for a finite interval. Not 10,000 feet. You don't have to drill the whole section with liner drilling. You just want a liner drill where you have the problem. You follow me?
Yeah.
So if you have a 6,000 foot interval and your problem is at the bottom 200 feet, you drill conventionally to where that problem area is, come out of the hole with your conventional BHA, pick up the liner and drill that problem area with the liner.
Thank you. I understood.
You're welcome. Good point.
And I think that is the last question. So
come on, more questions. Come on.
I mean, we might have a few shy ones amongst us, but
yeah, feel free. Email me and I'll reply right away. I love answering these questions because I support this technology 100%. For the right application, it's a brilliant solution. One thing I didn't mention, I'm sorry about this, it is compatible with managed pressure drilling and also continuous flow systems. Why is it compatible with managed pressure drilling? Because the drill pipe itself is connected to the surface, so you're sealing around the drill pipe. Liner drilling has been used very successfully with managed pressure drilling. Another technology it's compatible with is continuous flow circulation. The advantage of continuous flow circulation is that on connections, you're continuously pumping, which is great for drilling through depleted sands. So those two technologies are compatible. So it's a very versatile system. It's got its application.
Thank you, Steve. And I'm sure that everybody benefited from that. I know that there are a couple of students that are taking drilling as a subject right now. So this is, directly related to that.
Yeah, talk to your professors about that. See what they think.
Sounds good. Thank you so much, Steve. We appreciate the time. We
appreciate the opportunity, and feel free to email me or whatever. If I'll answer some more questions. I'm sure you all have some more. So.
I'll give them your email. Thank you so much.
All right. Stay in touch.
Of course. Sure. Take care. Have a good day.
All right. You too. Bye-bye.
Bye. Take care.
All right.